Hello and welcome to this presentation on VMware Private AI Foundation with NVIDIA. This is a technical overview, and I'm Justin Murray, Product Marketing Engineer at Broadcom. So our agenda here is we'll talk about some goals and terminology to begin with, and then we'll talk about why VCF, for private AI in particular, what the value of it is, some deployment options. We'll then get into rather new features, model store, and private AI services that appeared in 9.0. So to start out with, who are we addressing this presentation to? It's largely the VCF administrator, maybe DevOps people, site reliability engineers as well, who will be getting requests from data scientists for perhaps data science environments. And we want that conversation to be about VCF. So that's our purpose here, is to show you how VCF forms a great platform for doing data science on. And to do that, we're going to need to understand a little bit of the end user, the data scientist, the AI developer, a little of their world, but not understand them completely. We don't have to be data scientists at the end of this presentation, but we'll know a few terms and terminology surrounding that area. So the purpose here is to treat AI applications, Gen AI applications, private AI applications, just like any other workload in the data center, managing it through VCF administrators, just like every other workload. And so we may need the infrastructure architect who designs all this to talk to data scientists and show them how valuable this platform is. And I'll do that very shortly in the presentation here. So that's our key audience for this. Not necessarily the data scientists themselves, even though they may join the conversation. They may have a yes or no vote over the infrastructure, but we want to reinforce with the infrastructure people that VCF is a fine platform for doing AI on. And software architects will eventually use the product that the data scientist produces, a model effectively, to build an application, build a business application like a chatbot on it. So you may recall seeing VMware Private AI Foundation with NVIDIA before. We'll get into these parts as we go forward, and this will expand in 9.0 quite a bit. But the blue layer here is the one to focus on. That's the VMware Private AI Foundation with NVIDIA. That's running on top of VMware Cloud Foundation, which is the core piece that a customer needs to have. And I'll explain to you what a vector database is, what model governance is. I'll show you how the self-service automation works as we go along. And GPU management is a very important area because one of the things that VCF promises is to make better utilization of your GPUs. And that's only possible through better visualization of what they're doing. There's a lot of that to be had in VMware Private AI Foundation with NVIDIA. So a quick 7 or 8 topics in AI that I want to refresh your memory on or introduce you to so that you're clear on all the terminology that we're using in this presentation. So large language models, you are already using these behind ChatGPT or other Claude or other tools that present the possibility for you to type in a question and get an answer. Behind the scenes, there is a model. A model is a piece of software that has AI algorithms inside it. Those algorithms are called deep learning techniques. They make use of things called neural networks. And these things are trained on large pools of data, large quantities of data, every piece of data they can find on the internet, basically, the Library of Congress data, Wikipedia data. That is given to the model at training time, and we'll say more about this. And once the model is trained, it can then summarize and generate new content based on a user request made in natural language. That could be English or Spanish or Japanese or any language. Examples of this include the Llama set of models from Meta or Facebook, the Mistral models from a company called Mistral, and there are many others of these models. Some of them are open weights models, open license models that we can bring down from the source of them and use them in-house. Another important term is retrieval augmented generation. And what that essentially means is adding to the model a database that will inform the model or augment the model with real company data, private data. So this is a design that improves the accuracy and reliability of LLMs by allowing them to access information from databases and other sources. And this helps to ensure that the LLM is firstly aware of my private data, and secondly, able to present that data to the model for answering questions. And the key to doing this is something called a vector database. We'll explain what a vector database is. Think of it as Postgres with a new data type called pgvector in it. And the idea here is that the model and the vector database are working together to more accurately answer questions from users, because models on their own don't always answer the question with the correct data, especially if they weren't trained on that data. For example, we're producing 9.0 as we speak. Any of our internal documentation on vSphere 9.0, VCF 9.0 is not public yet, so it's private data. It might be stored in a vector database if we want to have somebody on a customer call respond to a question about what's coming, for example. So a vector database is a private database. We layer this on top of a relational database called Postgres. And it's used to store and index private company data. By index means provide optimal response on a query to give you a high-speed search based on whatever the context is in your query. Tell me more about GPUs in vSphere 9.0, for example. The resulting query results are then used in the machine learning model to produce the response, so that we're using one source of truth in this vector database to feed the model with the correct answer. So VMware Data Services Manager provisions these. It provisions a PostgreSQL database and a data type called pgvector on top of that. What is pgvector? It's an open source extension to Postgres that allows it to behave as a vector database. Vector database is a slight variant of a relational database that stores records that are numeric, streams of numbers. These are called vectors, and these represent the words in your text that you've loaded into the database. And there is a process for converting your words in your text into these numeric values. That's called embeddings, and we have a model for doing that as well. So entries in the vector database capture the meaningful semantic relationships between items in the data and similarities between data sets and documents. This document looks like it's got GPU information in it, for example. Coming now to VMware, a core piece that we offer is a deep learning VM. When somebody wants to provision this, a system admin, DevOps person wants to provision this to give it to a data scientist, we call it an AI workstation. It's a regular virtual machine with some tooling in it, Python, Conda, a set of deep learning VM images is shipped for these from VMware. And it's deployed as a template in the content library. And these images are used to create a deep learning VM for the data scientist when they request an AI workstation. A unique thing about these VMs is they've got virtual GPU profiles attached to them, so they can make use of the physical GPUs on the host. Two terms that you've probably heard a lot about in the industry are training and inference. For us, actually, training, it's important to understand it, but inference is where we're going to spend most of our time. So, as I mentioned previously, a set of data scientists feed large quantities of data to that machine learning model so that it can learn the patterns in the data. What patterns come up the most? Do GPUs come up in the context of VMware, for example? This is done repeatedly over and over again so that the model becomes trained on those patterns. And once it's trained, it can identify these patterns in different testing data. So data that it was not trained on, for example. So training models is somewhat similar to the development phase of software, but the goal is to produce an accurate model. And it's actually quite a big job, and we'll say why it's a big job in a minute. We don't expect too many customers to really do full-scale training, maybe a little fine-tuning type training, but not full foundation model training as Meta and Google and OpenAI do. So inference comes after training. Once the model is trained, we can now use that model in an application to recognize patterns and produce new text based on those patterns in my questions. So the model is now working with new data that it's generating, or perhaps new data that has been fed to it from a database that it's never seen before in its training. and it's classifying what it sees and predicting new words and sentences to generate new text based on the patterns it learned in the training phase. So inference is very important. It's the second phase in machine learning, really. Training comes first, but inference is the production phase of machine learning. So now you've got 7 terms here that help you understand all of the discussion we're going to have about why VMware VCF is so important for somebody who's practicing this. Now, large language models live in an ecosystem that sits around them. We've learned about vector databases feeding the models with source of truth data from our business. But somebody using that model is using PyTorch or TensorFlow or one of the other frameworks that are popular. They're using that in a Jupyter notebook, and it would be nice if that environment were all provisioned for them so that they don't have to worry about setting it up. And indeed, setting up the model as well, and that's what we do. Models don't just take text as input, as you see on the top right. They also take video and other mechanisms of data that feed the data into the model. And so models are now multimodal. They can issue text that describes what's in a video or in a photograph, maybe for an insurance claim, something like that. They can also take audio and analyze that. And the classic way in which you interact with a model, as you know, is through a chat or chatbot client. That's what we'll build as a simple example here. But there are other models involved as well. I've given you one already. The model that brings my text data into the vector database is called an embeddings model. We'll provision that as well. And the embeddings model is helping the main model in the middle here, the large language model in the middle, which makes use of a GPU to complete the answer to a customer's question. That main model in the middle, there is sometimes called the completions model, as opposed to embeddings model. So training one of these large language models from scratch, as I mentioned, is something that really the hyperscalers would do mainly today. It involves thousands of GPUs. It usually takes weeks and months of time, and it involves a large team of data scientists. So you can gather from this that training one of these models from scratch with all of the data on the internet, all of the data on Wikipedia and Library of Congress, it's a big job that is very high cost, several $1 million, consumes lots of energy, and it incurs the risk that you'll produce a model that's not as good as the other models out there. So your model may not be of the highest quality unless you've got a lot of expertise in your data science team to do this. So we're not asking our customers to do foundation model training or model training from scratch. Large language models are not perfect. They can sometimes do something called hallucination, which is the creation of an answer to a question that they think is the right answer, but is made up. It's not the right answer. They're not up to date in the sense that a model is trained for a period of time and then it's released into inference mode, but any data that newly appeared after it was trained is not known to it, so it can't answer those questions. And it has no traceability. It has no mechanism for us to find what the documents were that caused it to give you that answer. So these are all things that we need to fix, and we can apply various techniques to fixing them. Prompt engineering is one, a big field in itself, where you're giving the large language model some guidance in the question you ask of it. Fine-tuning is another, which is taking smaller sets of data than the big data that we just talked about, but taking some company private data and retraining the model, perhaps retraining just a part of the model. That's called fine-tuning. That's actually quite a tough job in some respects. The easier way to do this is retrieval augmented generation, which, as I mentioned, is the addition of a database into our system that feeds our large language model with clues about the answer to the customer's question, chunks of document that will give the customer some answers. So what this does then Adding the vector database in gives us validated information. We can update it frequently, so we keep the data up to date rather than having to retrain the model on the left-hand side. And we can have it the model cite the documents that were used, because the vector database can tell it which documents were used. So this kind of design is recognized across the industry as a great on-ramp to doing generative AI, a great starter application. And we'll show you a very simple example of this later on in this presentation. So how does it work? Essentially, I load my base private data into the vector database as a prerequisite. That makes use of a model called an embeddings model to do that loading. And we'll see in our private AI services that this can be done very simply. Now a question is asked by a customer or a user on a chatbot application that has been written by the AI developers that uses a large language model and a database together. And that question is converted into embeddings and issued to the vector database, and it comes back with all of the data sets, chunks of data that it knows are relevant to that question, that original question that the customer asked. So now we've got paragraphs from our documents that talk about GPUs on VMware, if that was the original question. Now we're going to take those results from the database and send them to the large language model, the completion model, and also send the original question, the original prompt. We're going to send that along with the chunks of data we got from the vector database, and the large language model is going to process them and generate the response. So this is the simplified retrieval augmented generation design. And this is important because a lot of our early customers are using this kind of technique, this kind of design pattern to build their first application. It's not the only application, of course, but it's an important one. So now you understand the importance of the vector database. We provision the vector database through VCF automation on your behalf. And now you know that there are multiple models involved, and those models may have different versions and different level of quality, quality being accuracy, performance, absence of bias. So model governance is very important. We'll do that based on a model store technology that we have that allows us to store different versions of the models according to our testing. Self-service and automation is a big area of VMware Private AI Foundation with NVIDIA. This is the ability to provision the deep learning VM and a Kubernetes cluster, if need be, automatically for an end user, whether that end user be a system admin, a DevOps person, or even a data scientist, with the minimum of intervention that they answer one small set of questions and we provision it for them. And as I mentioned, we want to watch how the system behaves as far as GPU consumption is concerned. And there's a lot of that in VCF operations and in vCenter for monitoring what's happening. The components at the top in green are NVIDIA generated. They're NVIDIA pieces of software. The retriever, for example, gets data out of the vector database for us. The NIM microservice runs the model that it sees in the model governance for us. NVIDIA blueprints are example applications that can be spun up quickly using a set of containers. These things, NIM microservices and NeMo retriever, are just containers stored on the NVIDIA GPU Cloud portal site, and they're retrieved by our automation technology, either from the NVIDIA GPU Cloud or from a private repository when we're automatically creating a deep learning VM or a Kubernetes cluster. And in the Kubernetes case, we have operators like the NIM operator to take care of the life cycle of the microservices and containers on the left-hand side. So that's a very quick look. We'll be getting into this in more detail. All of this is written up in documents on our site, but also a variety of OEM vendors, as you see at the bottom, Dell, HP, Lenovo, Supermicro, Hitachi, and Fujitsu have all written documentation, some of it very detailed reference architecture documentation that describes this. Now, this is how VMware Private AI Foundation looked when we shipped it first at VCF 5.2.1 in May 2024. In future releases, it will expand, as you see here. The green layer is pretty much the same, but a new layer has appeared inside VMware Private AI called Private AI Services. PAIS. And these are composed of a model runtime, an agent builder, and a data indexing component. And these things operate one level up from your deep learning VM or Kubernetes cluster. Your Kubernetes cluster is hidden behind the scenes of these new services. And what they do is give your model a lifetime in model runtime. They index your data for you, the data indexing technology that's not shown here, and they allow you to build an agent or an application that uses the model and the index data to generate your application for you. So really model as a service here in service of application builders. That's where we're going with this in the 9.0 private AI services. So why is VCF important for private AI? Well, we answered that question if we look at the end user of our automated deep learning VMs, Kubernetes cluster, and our private AI services. And what those folks are confronted with is model selection, determining from a variety of models that's out there on the public websites, portals like Hugging Face, for example, or NVIDIA GPU Cloud, which model can I bring down and run for my business? Which model is high quality? They have a lot of setup to do that. They have to run the model. They have to generate the tuning steps for the model. There's a lot of work involved in setting up a model. And then they have to build a RAG design, which, as we've said, is a combination of our model plus a vector database. And then an application has to be built that consumes that model. This might be the job of the data scientist. It might be the job of the application AI developer using the model the data scientist created. And so this is going on in multiple teams by multiple people with different models, different data sets, and different levels of quality, different levels of maturity in lots of different places throughout your enterprise. And so the reason VCF is so important is because VMs and Kubernetes based on VMs are the ideal platforms for managing all this complexity. I don't know how many times data scientists have said to me, I wish I could control the version of Python that I'm using more carefully. Well, if you've got that built into a template VM that you can recreate at will, or built into a Kubernetes template that you can recreate at will, that makes your life a lot easier. There is more than one model involved. There's more than one setup, more than one application being built. And so the diversity and the rate of change and the rate of innovation that's going on in this world demands a platform that doesn't tie you too tightly to the hardware. In other words, abstracts the hardware and abstracts a lot of other things away, and that's VCF. That's why VCF is so important here. It's also important for a second reason, and that is that data scientists in the past, when they've worked on bare metal, some of them still working on bare metal, have had to manage the automation themselves, the monitoring, the serving infrastructure, the machine resource management, the GPUs, for example. They've had to manage all that themselves and set up the networking, the storage. That belongs in corporate IT under the charge of people who've been doing this for years in the VMware world. Instead, the data scientists should be focusing on their models, data verification, data collection, and how the model is analyzing their data. Real data science. So we want to take the burden of managing all this away from the data scientist and put it in the hands of another group of people, IT admin, system admin, SRE people, DevOps people on the left-hand side. So what are our deployment options with private AI? Well, because private AI is based on VCF, we will have a management domain into which we will put components that influence the behavior of VCF automation, operations, and data services manager. And then we ask our customers to set aside a workload domain which will contain VMware Private AI Foundation artifacts like deep learning VMs or AI workstations deployed into a cluster and Kubernetes clusters deployed into either the same cluster or a different cluster. It's up to the user to decide that. And the reason there are two things here, deep learning VMs and AI Kubernetes clusters, is because we believe that the testing of models will be done in deep learning VMs or AI workstations. An AI workstation is the name used in automation for the deep learning VM. So we might want that deep learning VM to be separated off from the rest of the IT, because we're testing new models there for vulnerabilities, for harmful behavior, and we need to keep that in a safe place. So development and testing of models goes on in deep learning VM. Once the model is reasonably well tested, we would bring it down from our Harbor repository where we store it and bring it into a Kubernetes cluster for scalability testing. So both of these things, that the AI workstation, the AI Kubernetes cluster, contain NVIDIA components, containers or microservices, which help the data scientist to run their model or to augment their model with a vector database. So that's the high level. Now, going a little deeper, we know that AI Kubernetes clusters are composed of multiple VMs. Each VM represents a node in the Kubernetes cluster. We provision these VMs through automation for you. You don't have to provision them by hand. And within a VKS cluster, VMware Kubernetes Service cluster, we can have a set of namespaces, one for the GPU operator, for example, another from the NIM operator, and a set of pods run in those namespaces, pods being collection of containers. And we'll see these pods and what they contain in a short period of time. Inside the AI workstation, this is really a deep learning VM. We have a simpler picture. We have Docker to run our containers. They're the same containers that NVIDIA has at their NGC. And a new piece here is Data Services Manager to provision all the VMs needed for PostgreSQL with a PG Vector extension. All of this is running as a result of Supervisor Cluster being activated on our cluster. Supervisor cluster, as you know, is a curated Kubernetes cluster itself, carefully integrated with vCenter, that allows us to build new things like VKS clusters on the far left, or AI workstations. We'll be using that supervisor cluster to generate all these things as we go forward. And as part of model governance, we're going to use Harbor as our repository for models. Up to now, we've been using Harbor as a place where containers are stored. Containers need a repository, and particularly if we're operating in an air-gapped or disconnected environment, we will need a local container repository to keep all the NVIDIA containers that we've downloaded previously so that these things can be generated. Well, we're using Harbor for another purpose here, which is to store the models that we test and prove out and claim that they can be used in our enterprise. So that's done here. Okay, so 3 deployment options here. Do our deep learning by hand, which is a possible option, but it requires you to do a lot of work. AI Workstation does that for you, and does that for you particularly in the development phase of an application or even a model. AI Kubernetes cluster we see as the more mature end of the life cycle, where I've already tested the model, I've developed an application on it like a chatbot, and I want to deploy that now at a level of scalability that's one level up from just a single VM. A single VM is my AI workstation. So development covers the AI workstation. Production or production testing for scalability is the AI Kubernetes cluster. And as we go up this stack, we have more and more automation help to take some of the burden of generating all this away from the SRE or IT admin. All of this, of course, is working on a cluster of servers in a workload domain, and that cluster has some nodes with GPUs attached to them. Not all nodes need GPUs attached to them. Some models will work without a GPU, for example, but some of them do. And here's what this looks like inside VCF automation. So this was VCF Automation 8.16, which shipped with VCF 5.2.1. And at that point, we had 2 very simple catalog items here, which are configured in a set of steps called the Quick Start steps, which are a set of prerequisite steps that the SRE or DevOps person takes before any end user uses this. The end user could be DevOps themselves, could be system admin, or it could be even a data scientist that's willing to go into the screen and request an AI workstation. And as this has grown, more and more varieties of these have appeared. Instead of having just an AI workstation on the far right, we have an AI RAG workstation that contains a vector database. We have an AI Kubernetes RAG cluster, third from the right there, that has both the model and the database ready to go inside it. And the purpose of these catalog items is so that somebody can make a simple request for one of them and not have to do a lot of work to get their end result. The quick start process I mentioned is a preamble to that. And when I'm in the quick start, which is the setup phase for all this, I'm deciding which Kubernetes release and which amount of GPU am I going to allow people to use. In this case, we're going to deal with a model from Facebook called Llama 2 13B. 13B means 13 billion parameters, for example. That's a decent sized model. 70 billion is a very popular model to use nowadays for production applications. But here I'm saying that you're going to get 2 H100 GPUs in the lower green box there when you provision this catalog item that I'm building now. So I'm restricting the amount of GPU power anybody can get when they choose one of the catalog items. And I'm going to switch on UVM, which is a unified virtual memory facility that is needed to run some of the NVIDIA components here. So I can enable DSM at quick start time so that I can provision not just the deep learning VM or the Kubernetes cluster, but also provision the capability of having a vector database. And that vector database might be a brand new one, or it might be an existing one. So you can see here, these are customized catalog items to do exactly that, provision DSM with my setup. And when I'm doing database provisioning, I might want to choose a new database or an existing database. And here's an existing database. All I need from this is the connection string to supply to the other components so that they can retrieve data, especially the Nemo retriever can retrieve data from it. So here now I'm choosing the RAG station options, and I'm an end user now making a request for an AI workstation on the far right there. So here are the things that I need to decide at AI workstation creation time. Firstly, which VM class from a limited set of VM classes that the SRE person, DevOps person has constructed for me, which of those VM classes do I want to use in this particular request? And here the user has said, I'm going to use a vGPU, one A100, 40 gigabytes in compute mode, C for compute mode. And this is now going to be provisioned onto my deep learning VM or my Kubernetes cluster for me. I need to supply two more things, a password for the workstation for somebody to log into, and I need to supply the NVIDIA API key, which is something I've got from NVIDIA as a result of getting a license access to NVIDIA AI Enterprise. I can choose to switch on metrics here and switch on Jupyter Lab authentication. When this deep learning VM is really provisioned, it will have Jupyter notebooks running in Jupyter Lab, and I may wish to restrict that to somebody who's authorized. So I hit submit, and that goes off and provisions for me. These are just other custom examples of this. And what happens now is that the deep learning VM image that was loaded by system admin into the appropriate content library, that deep learning VM image is created. The image has Ubuntu as its operating system. It is set up correctly for NVIDIA virtual GPU usage, which allows me to share GPUs among two or more VMs. It has Docker to run my containers, and it has Conda and PyTorch for the developer to use. And that first boot time, the NVIDIA GPU driver, virtual GPU driver, will be downloaded either from NVIDIA GPU Cloud or from a local repository in which I've placed it, and a bundle of software to satisfy this AI workstation request will also be downloaded. This is called an NGC software bundle. This might contain PyTorch plus the Jupyter Notebook, for example. So there's a variety of bundles that I can configure to download into my deep learning VM. And let's see that in action now before we go on to this. Okay, so I'm going to do a little demo here. This is part of a hands-on lab that you can choose to use if you come to our hands-on labs. And I'm going to deploy an AI workstation here. And I'm going to put it into a mode here. So let's choose one of these requests. Let's take the very simple request that came out first thing. We've chosen a new project, we've chosen a deployment name, and we've given some commentary here. And here is the choice of VM classes. My choice is restricted to just 2 full A100s in this case. The system admin has decided this and created these VM classes to give you either 1 A100, 2 A100s, or 4 or 8, or even a part of an A100. The data disk size I've chosen, I enter my password, I choose which package of software. The simplest package of software is PyTorch, and I'm going to choose a more sophisticated version than that, Generative AI, and I'm going to supply my key, my NGC API key, and now the system is off and running, deploying my deep learning VM that backs my AI workstation, and I can see it operating inside the supervisor and generating all of the components that are needed for it to work here. That takes a few minutes, and I end up at this page after the automation is completed. And here is the link into my application now running in that deep learning VM with a Jupyter notebook, PyTorch ready to go, and a sample RAG application deployed in there. I can SSH into it or go in there by other mechanisms. What happened at the infrastructure level was a deep learning VM was created inside that namespace that I gave a name to. This is a namespace now seen in vCenter, and this particular VM has 2 Grid A100 40Cs attached to it. It's not uncommon for somebody to do this who's running a model, especially a 13 billion or 70 billion model might require more than one GPU. If I do an edit settings, I can see those 2 GPUs have been fully allocated to me as PCIe devices, and now I can go off and use this and SSH into that deep learning VM. I'm now inside my deep learning VM. I'm looking at how the GPU driver was installed. That's fully done for me, either from the remote site, NGC, where the driver is stored, or from a local repository. I can look at the code that was done to do this. And secondly, another script was executed to set up my model. And I can see exactly the details of the model that was used here. And because this is a deep learning VM, the very last line of this script says docker compose -f enterprise rag docker version there, and a rag.yaml file, which is set up for us. What that did was started 5 or 6 containers with Docker to build me a RAG application. And those containers are shown here. The second one from the bottom there is the Nemo retriever, which we know retrieves data from a vector database. The Nemo LLM inference microservice, third from the bottom, that's the NIM microservice, and the others on top there are the other actual application user interface containers. So we can see all these containers, and we can actually exec into one of those containers and see exactly which model is run. On the right-hand side there, in the second line, you see Llama 2 7 billion. That's the model that's running. It allows us to use that model through an OpenAI API, which you'll hear more about later. And so we can see exactly what's happening and what the parameters to our model are. If we look at the particular YAML file, you can see match batch size, input length, output length. These are all tunable parameters that a data scientist would use. Okay, let's stop here. We could use a chatbot to talk to this application, but let's leave that for now and go back to our presentation here. So what was happening under the covers was the text inside the green area on the right-hand side is being used. This particular example is using Llama 2 13 billion parameter with various options on it there. The reason I'm showing you this is you can actually edit this if you want to and create a new version of that catalog item such that it's using a completely different model, a completely different setup. You have the freedom to change this. And you can choose lots of different models from NGC, the NVIDIA GPU Cloud, or from Mistral, or from Facebook. Whatever model you choose to be appropriate to your business, this would be a data scientist decision, can be done here. Okay. If you wanted to know what are the ideal GPUs to use with any particular model, NVIDIA has a site here. You can copy that URL at the bottom and take a look at it. It has a support matrix site to show you for any particular model, in this case Llama 3.1 8B that you see about 10 lines at the bottom of the screen there. Llama 3.1 8B. They're recommending that you would use an H100 or two H100s to run that for high efficiency. And this, of course, is a result of testing that they've done. Okay, deploying an AI Kubernetes cluster, we probably won't do live here to save time, but what's really happening under the covers is containers from NVIDIA, represented on the right-hand side there like the GPU operator, that it effectively takes care of the virtual GPU driver for me, and network operator that sets up networking for me. Along with the NIM, the inference microservice, and the retriever, they're all downloaded from NGC or from a local repository and installed into pods in the Kubernetes cluster. That Kubernetes cluster was created by automation for me, so that's already generated, and then the data services manager is set up to provision Postgres and provision PG Vector, which is a new data type that goes into Postgres, automatically for me in a secure way. And one reason why Postgres is a great choice as a basis for your vector database is Postgres has been around for several years now. It has replication, it has backup, it has role-based access control, which all are needed for that private data that we're going to put into the vector database using the NeMo retriever or using data indexing in our own services. Okay, so I won't do this demo in the interest of time. It's very similar to the one we saw earlier. You just have a little more choice as to what the worker nodes do, whether they be GPU worker nodes or not. All of this is dependent on some setup being done first, in particular the quick start, and some licensing keys that you need to get from NVIDIA. And in our longer deck, we have a discussion of those licensing keys. But here I'm going to come out of presentation mode and go forward to show you some of the new things that are seen in VCF 9.0. So I'm going to start with Model Store. This actually shipped in VCF 5.2.1. And what this is essentially using Harbor to store models that I've tested in the left-hand side of my diagram by pulling those models down from a public domain, like Hugging Face, which is the global repository of models, NGC, which is NVIDIA's curated models, or some other site like Facebook, for example. Pull those models down, whichever the data scientist wants, using the NGC CLI or some other mechanism, and test that model out for accuracy, for handling of bias, for safety, not answering dangerous questions, for example, all of the things that the data scientist would want to test a model for. And once they've tested and validated that the model is good and performs well and is accurate, then they will send that model up into the Harbor repository, which is our model store, using a push technique. We provide a CLI that has a push command to it and also has a pull command on the right-hand side there, where now somebody has decided, I like that 13 billion model that was pushed up yesterday. I'm going to test that model out with my application. And so I'm going to bring that model to life using a new service in Private AI Services called Model Runtime. And we'll see how that works in a second. Model Runtime is a way of giving the model life and allowing people to use it through a URL called an endpoint. And we'll get into that. Separately, we will index the data. You heard me talking about indexing the data through NVIDIA NeMo Retriever. We can also index the data through a different model that we've chosen, such as an infinity model with running an embedding model. Once we've got our model in the runtime with an endpoint and our data indexed in the vector database, now we'll use the agent builder technology to build an application. All of this is happening in application development and testing on the right-hand side. So that's the full picture. Harbor is giving us different projects for different parts of our enterprise, and within each project I can store a repository. I can have a repository, and inside those repositories I will place my models. They're just files that are controlled. There is version control over them. It's a place to establish that I've got quality models here. This is what it looks like. The top model there is public. Anybody who has access to Harbor can pull it down. But the other models are private. They're for specific uses that only people who have the appropriate access rights can get them. You would have to build something called a secret, an object called a secret, in order to pull one of these models down. So you have the notion of public and private models inside Harbor. And so this simplifies model management, provides tools and processes that simplify the storage of models. It uses an industry standard called OCI, Open Container Interface. We provide the wrapper around your model to make it OCI compatible, and it allows us to, across different namespaces, pull the models down and use them. So this is a key component of the new private AI services in VCF 9.0, and we'll look at that briefly now. Our objective with this is layered on top of Kubernetes, on top of the deep learning VMs that we've been talking about, and hiding those things away, we can streamline the deployment and management of RAG applications through using services. And the particular services are the model runtime service, the data indexing and retrieval service, and the agent builder service, all of which have a GUI that is accessible to us, a CLI so that I can use them through the command line, and an API so as I can actually program these things independently of the GUI, independently of the CLI. And as mentioned before, the model store is a place for packaging and distribution of models, storing of models. The runtime is a place to use an inference engine to bring a model to life. And once my model is alive and running in an inference engine, which is running on Kubernetes, by the way, then I have an endpoint for that model. I have a URL for accessing that model to ask it to do something for me, to predict a new sentence, for example, or deal with this new data. Now, separately to the model, I want to take my private data and store it in the vector database, and the process of organizing the data so that it is ready for queries in the vector database is called indexing. There's quite a lot of technology to this, but indexing is essentially done by a different model called an embedding model, and we set up another runtime for that, another endpoint for that. So we'll see that in a second. Once I've done those two, generated my model in the model runtime, brought it to life, indexed my data, placed it into a vector database, then Agent Builder kicks in, and this is how I build a RAG pipeline to be used by an application on the right-hand side there. So let's look at these in the sequence then. The model store is the master directory of any validated models, any tested models. The model runtime is where I create my model in running form from an entry in the model store. And so I'm given an endpoint when I do that people can use to access the model. I create another endpoint for my embedding model that's used in data indexing. My completions model and my embedding model are used by the agent builder to create an application. So that's the big picture of all of these services that we saw just now. So looking at model runtime, this is the process of bringing a model to life from an entry that is static in the model store in the Harbor repository. So what happens here is each model is run in an inference server, and that inference server is a container that's running in a worker node on a VKS cluster that's been created for you. You have not had to create this VKS cluster yourself. The runtime does it for you. So it's hidden away from you and you don't need actually to see very much of it. For every model endpoint, there is one or more worker nodes, VMs, that support that model endpoint. So for my completions model, my major model, there's model endpoint 1. For my embedding model, there's model endpoint 2. They're running on different nodes, different collections of nodes called a node pool in a VKS cluster under the covers. And they're exposing a model endpoint, which is a URL for accessing the model. So that's what's under the covers of the model runtime. But there is also an API gateway in that runtime that allows me to establish that the user on the left-hand side, whether it's an application being run by a user or a CLI or an API call, that this question is allowed by for that user. And if the question succeeds through authorization and authentication, which copy of the model is it going to? Is it going to copy 1 of the Llama 3.1 completion model, or is it going to some other copy of that model? So load balancing across my models is important here. So benefits of using this runtime then and the API gateway component are I now have authentication and authorization of my request to the model. I obey the OpenAI compatible APIs. That's important because I might want to bring an application down from OpenAI deployment in the public cloud and run it locally on premise with private data. That would mean the application would need to use OpenAI APIs, and that's exactly what our model runtime allows you to do. That's a stable API interface, and we also allow load balancing of requests across copies of the model if need be. So moving on to step 2 of 3 here, we are now talking about the private data, and our target here is to load that private data in the correct format into the vector database. In order to do that, I want to identify where the data is coming from. That's the data sources. I want to collect those data sources into a collection called a knowledge base, and I want to execute data indexing, which is the process of chunking up the data and translating the data into numeric form to be stored in the vector database at the end of this process. So here you see various data sources on the left-hand side: SharePoint directories, SharePoint files, Confluence pages, Google Drives with files inside them, S3 compatible buckets with PDF data in them, or a local file. Any one of these can act as a data source to create a knowledge base. And those data sources are going to be looked at, such as a PDF file that describes GPU support on VCF in the middle there in red. It's going to be indexed in the sense that all of the documents are broken up into text chunks. You can see the text chunks in the middle blue layer there that has the Latin phrases in it. These are smaller things like sentences or paragraphs within the documents. And then each of those chunks or paragraphs of data, the chunk can be any size, by the way, you can decide on that. Each of those chunks is translated into a numeric form called embeddings that you see on the bottom right-hand side. And those things are loaded into a vector database, and now the vector database is ready for queries against the data that came from the documents. So that's the data indexing component. We'll see retrieval when we go to the next step. And that next step is building an agent using our agent builder. And in particular, we're going to build a RAG agent. So what is an agent? It's an autonomous system that performs specific tasks, makes choices as to how to route or route an incoming request, for example. It's powered by LLMs and domain knowledge and works independently to make decisions. The decision we're going to ask our agent to make is, how would you route an incoming question to the vector database or to the large language model, and how would you connect those two together? So it optimizes by automating tasks within its scope. So we're going to build a simple agent here that understands the design pattern that I introduced to you at the beginning, which is retrieval augmented generation. And this combines a large language model with a retrieval system to fetch in real time relevant information, enhancing the accuracy and context of the generated response. So at the bottom, you see the model endpoint that we created as a result of the model runtime, bringing our model to life, and the knowledge base was indexed with our private data. It's going to use both of those. So here's the flow, very similar to the flow we saw earlier, but the difference here is the RAG agent is making the decision when it sees a question come in from a user using a chatbot on the left-hand side. The query comes in at number 1. It's handled by the RAG agent and sent as a similarity search to our knowledge base. Any records that have a similarity to the incoming query are returned. Those were loaded up at 0 time on the right-hand side before any of this query happened. There was a loading phase of data. Any relevant records or chunks or indexes are returned in number 3 there. The RAG agent sends the original question plus all of the chunks which are relevant up to the large language model endpoint there. That's our running model in the runtime. It of course, was originally an entry in Harbor, which was brought to life, and the response is generated there at number 5 to the question based on the input prompt at number 4 and all of the data from the vector database that was allowed into the LLM with it. So now we've got our answer. We return a response at number 6 there. So this agent clearly uses the completions model endpoint. It uses the original prompt or instruction that was given to it, and it uses data indexing and retrieval, the knowledge base that was indexed to fetch data from our vector database. And it also allows us to keep a chat history of everything that's been done in chat, so that if the same question comes in twice in a row, we don't have to go through the full process to answer the question. We've already got it. So this is the big picture of how they all connect together. As I said, we pull a model down from online repositories like Hugging Face and Meta on the far left. We test it out in a deep learning VM. Once it's tested, we put it into Model Store. To bring that model to life, we create a model endpoint in the model runtime. We index our data separately using an embeddings model, which is also running in the model runtime in a separate place. It's a separate model to our main completion model. And at application building time, we run an agent builder to take our running completion model and our index data and bring them together into one place and supply that end result to the customer application on the right-hand side. So the user experience here, there's a lot of setup help for you for a VI admin, a lot of steps you can go through to set all this up. And here's what it looks like once you've done your setup. You've loaded in the private AI services on the bottom left-hand side here. You've loaded in other services as well. You've used the VM service to create the VM classes. And now we're ready to create catalog items using the quick start, as I mentioned. And here are the private AI services that we just saw in the user interface. And of course, we've seen this flow just now, the model store, the model runtime, data indexing, and agent builder. And here is the choice of catalog items that you might find in VMware Private AI Foundation. Here's a request that we saw going on. Here are all the places you can get models from. You can download them in different ways. And here's the creation of a model endpoint using the model runtime service. So we've already uploaded our model to Harbor, and now we're creating a model endpoint with a routing name. We're using a URL for that model that came from Harbor, and we have various parameters here. Now that we've got it, we're going to create a knowledge base from our vector database using a particular embedding model. In this case, it's running on Infinity. And finally, so we select the model there. With all that, we can use a variety of different pieces from the open source community and generate an application that's eventually running on the supervisor in a VKS cluster in a pod running VLLM, as you see at the top left-hand side here. So that's the full big picture of the private AI services as seen in PACE operator, PACE config there. Those were configured in at installation time. At model runtime, we've generated a new VKS cluster that has worker nodes serving our two different models here, our completion model on the top left, our embedding model on the right. And that's it. Thank you very much for your time today.